The last little thing we're going to talk about related to Lewis diagrams is structural formulas. Structural formulas are like a Lewis structure, which was the model of that, but instead of showing all the bonds and all the lone pairs, structural formulas just show the bonds. So sometimes they're going to give you just the bonds and they're going to assume that you can figure out how many lone pairs should be there based on what bonds are there. Some molecules can't be represented with a single Lewis structure because of how their bonds are placed. In these cases, what we'll do instead is we'll draw multiple different Lewis structures and we'll connect them with double-headed arrows, and we call that a resonance structure. An example of this is ozone, which is 3 O's. So you're going to have those 3 O's connected with bonds, except that there will be one double bond and then this guy will have a lone pair, and then one single bond. And the result of this structure is that double bond can be on either side. So we can't just draw it on one side and call that our structure. We have to draw a resonance structure, so we draw that double-headed arrow, and then we draw the same structure on this side, but instead the double bond is between these two oxygens instead of the first two. Which does matter, which two oxygens you show it between. So when we draw that double-headed arrow, what we're essentially saying is that this atom or this molecule can take either one of these structures. And in reality, in nature, it's really more of a hybrid between the two, but to represent it, we draw it like this. In the real world, atoms don't always form discrete molecules. So what I mean by that is when we draw these Lewis structures, we draw them as independent molecules, right? We're like, this is a molecule of carbon dioxide. But in the real world, one molecule of carbon dioxide doesn't always exist by itself with nothing else happening to it. Very often, compounds consist of tons of identical molecules together, and then those identical molecules are actually being held together by other forces, which we will call intermolecular forces. And sometimes, even more than that, those compounds are actually bonded into networks instead of being individual molecules. So you might have more of a lattice or a structure where it's multiple of these molecules bonded together to each other to form this compound. So it's not always as simple as the way we draw them here in class. That's all the notes we had to finish. We just didn't quite have enough time to finish them yesterday, so we're going to stop them there.